Good morning, everybody, and welcome to the first of the weeds talks in this year's Biosecurity Bonanza, put on by Manaaki Whenua, Landcare Research. I should just quickly add that if anyone is returning from last year's talks, I do apologise that I don't have my mushroom collection in behind me like I did last year, but I've had to change rooms. So anyway, moving on, I'd like to welcome Ronny Groenteman. Ronny is one of our sort of becoming more senior scientists in our team these days, and is running a lot of our research program, which was previously run by Simon Fowler and our team. So Ronny's going to talk to us about rapid evolution. So I shall let Ronny take it away. Thanks, Ronny.
Morena, tēnā koutou. Thank you, Hugh, for this introduction. So this work that I'd like to talk to you about today, this is work that is funded by the Strategic Science Investment Fund that we received from the Ministry for Business, Innovation and Employment. And in this funding, we have several pieces of work, several programs, and one of them is about increasing and improving the safety and effectiveness of weed biocontrol programs. And in that, one of the focus areas that we work on is the area of rapid evolution. And what does that mean for weed biocontrol? So evolution happens in biological systems. Biological control is no different, and so we can assume that evolution is inevitable in biocontrol system, and it is inevitable for both the biocontrol agents and for the host plants. And I will mostly focus today on the biocontrol agents side of it, and I will only in the end touch a little bit on the host plants. Not only is rapid evolution inevitable, we have a recent review that shows that it is probably the norm. So it is the rule rather than the exception. We should expect adaptation to happen in weed biocontrol systems. And when we think about rapid evolution and biocontrol in the same sentence, we tend to ring some alarm bells, and we tend to think about agents that might expand their host range, or agents that through captive rearing might end up being unsuitable, being reared into individuals that are unsuitable for, maladapted for the environment that they will be released in the end. But in fact, rapid evolution and adaptation can be beneficial in biocontrol systems in several ways. And one of them is potentially that an agent that is initially a poor performer in the novel environment that it's been released into adapts to subsequently thrive in that environment. The system that we'll look at this aspect is the example of the heather beetle in the Tongariro National Park, the Central Plateau area of the North Island. And this is work that has been going on for over 20 years. And Paul Peterson in the photo here is the one who's been doing most of this work. And this is also a good time to let you know that Paul will be talking about other aspects of this system in his presentation tomorrow afternoon. So if you haven't registered for that and you want to hear more about the heather beetle system, I do encourage you to register for Paul's presentation. The aspect that we're going to talk about today is what is going on with the establishment rates of the heather beetle and whether there's any adaptation happening in that aspect. So the heather beetles were first released in the national park in around the 1990s. And in the early days, out of 18 sites where the beetles were released, they pretty much failed to establish everywhere except for one site. So it didn't matter whether the size of release were big or small, they all equally spectacularly failed to establish except that one lucky strike. From that one lucky strike, there were further releases made, so redistribution out of that site. And then we see already an increase in the rates of establishment, so getting up to about 40%. We started with about just over 5% success in the 1990s. We're now looking at about close to 40% establishment rate. And this time there is also a role for the size of releases. So larger release sizes have a better chance of establishment. In the 2000s, populations start to grow exponentially, and Paul can show you incredible aerial photos of that. And the park is starting to get covered slowly with heather beetles. And then Paul notices that the heather beetles are not only exploding in their populations, but also new foci are starting to pop up exponentially in areas where there haven't been releases made recently. And those areas include parts of the park where the beetles were released in the 1990s and failed to establish at that time. Now they're popping up there spontaneously. What is going on? It was very clear that if we want to find out what's going on, there was a need to set up an experiment urgently. And that's what Paul did with 30 releases made, trying to get ahead of the front of the beetles that were moving pretty fast. There was obviously a risk that those release points were going to be swamped by the beetles, by the front, and it was really a matter of now or never. And in the photos here at the bottom, what you can see is an area of the park covered in purple heather blooming, and an area on the right where the same area, basically after the beetles, the front has been through and decimated the heather. So all you can see is defoliated heather. Indeed, quite a few of those release areas, those new release areas, were swamped by that front that was moving, and more than half of the points basically either were certainly swamped by the front, or we couldn't be entirely confident whether the beetles that remained there were from the new release or from the front. So all of these points that were definitely swamped or potentially swamped were excluded from the analysis, and even then, with 14 points left, we can see a really striking picture of what's happening with the rates of establishment. In the graph here, you see the rates of establishment in the 1990s, most far on the left, with just over 5%. In the 2000s, getting up to 40% establishment success rate. And then in the recent years, only 2-3 years ago, we're looking at close to 86% establishment rate, and this is a conservative estimate. So its establishment rate has increased, and dramatically so. What is going on? What is driving this dramatic change? And can this be an adaptation? Ideally, in an ideal world, we would be able to test this with molecular tools. And I think today we're quite used to hearing about genomic testing and how you can, on a daily basis, get the sequencing and link individuals to one another and see what the change, the link of changes has been in the genome. Unfortunately, beetles have a slightly larger genome than a virus, and we're not there yet with molecular tools to be able to tell us very small changes that may have occurred. And we're just not there with the ability to tell definitively with molecular tools whether an adaptation has in fact occurred. What we can do instead is look at what are the alternative explanations to the increase in establishment rate, and whether those alternative explanations are better or whether adaptation is still a more plausible explanation. So what are these potential alternative explanations? 3 of them that we're looking at here. One of them is that there's purely been an environmental change. The environment in the park is somehow better now for the beetles. Another alternative is that this is purely a matter of numbers. The populations simply increased enough and the establishment rates are better. Or is it somewhat a combination of the increase in the numbers combined with some adaptation, something that happened with the beetles that enables them to overcome whatever it was that gave a barrier to them in the early releases in the 1990s, so some kind of adaptation. How do we go about testing these alternative hypotheses? Well, first, let's go look at the environment component. One side of that environment component can be the climate, and it was originally considered that climate could have been a barrier for the beetles' establishment. The winters in the Central Plateau can be pretty harsh. And what we also found later on was that the springs are absolutely erratic, and the temperatures can go in a single day from a deep minus to a quite nice plus in one day. It is quite possible, though, that in those 3 decades since the beetles came into the country, that the winters have become milder. That would be not surprising. And then is it also possible that the springs have become less erratic? That's probably less likely, more likely the other way around. It might be that springs are even more erratic than they have been 3 decades ago. So we've got data loggers now along the same areas that we've had them in the past, and we can find out what the changes in the climate have been. Another component of environment is plant nutrition. And heather is notorious for being low in nitrogen level. It's not a very good nutritious plant for insects that try to eat it. And not only is it a poor plant, poor nitrogen level, we discovered earlier on that the levels of nitrogen in the heather in New Zealand are even lower than the levels in the native range. So very, very poor nutrient plant. And then the question is, has that changed? Has the nitrogen level increased in heather in the 3 decades? And the potential driver for that would be air pollution. And we know that air pollution has increased in those 3 decades. And can that have changed nitrogen level? Watch this space, we're looking at that. Is it a pure numbers game? This one is a bit hard to swallow, because if it's a pure numbers game, how would that explain the changes in the rate of establishment? I mean, we could expect, if it's just a numbers game, then we can expect more areas where there is establishment, but not at a higher rate. So that one is not easy to reconcile. We can't really believe that one very easily. But then what if it is a combination of numbers and an adaptation? And what would that adaptation be? So it could be physiological adaptation, and that would be potentially in body size and fat reserve and low frost tolerance that the beetles experienced when they initially were released in New Zealand. And we're talking about physiological frost tolerance here. This is about the components in the fluid system, in the hemolymph, the blood system of the beetles, the antifreeze. And as far as body size, fat reserves, and the frost tolerance, the beetles that were released in the 1990s were small and had low fat reserves, and they lost their frost tolerance within about 2 days after emerging from winter hibernation. And those beetles did come from a very limited genetic stock, and that is because they did go through a severe bottleneck during the rearing in containment. This was because this population had a disease that needed to be rid of. The disease was rid of, it's not in the population, but the outcome of that was a bottleneck in the rearing and a very small genetic diversity being released in the field. So has anything changed in those physiological components? Or has there been a behavioral adaptation to frost? If the beetles are up on the plant when it's frosty, they freeze. Have they changed their behavior to drop down to the leaf litter? This one is a little bit more difficult to test, and we're not quite sure yet about if and how we would go about that one. But the idea is to look through those alternative hypotheses and see, is there anything in there other than adaptation that is more plausible and can explain why the beetles are establishing at a higher rate now? Okay, what are we going to do with this information? We're studying that heather beetle system quite vigorously, but what is it going to tell us about biocontrol systems? It might help us understand why agents fail, and is it a failure due to lack of adaptation? And if we think that adaptation in biocontrol systems should be the norm rather than the exception, then can we use that knowledge to drive adaptation faster in the direction that we want it to go? What can we do in our release strategies to drive adaptation if we accept that adaptation is going to happen at some stage? So there's a few ideas that we can think about managing our sources of release differently. And a caveat that all of these ideas are not tested yet. So this is perhaps an area for future research. One of the things we could do is avoid mixing release sources to stop outbreeding depression. So when we have we have agents in containment from several populations, our best practice at the moment would be to mix the genes so that we get a most diverse population that we can getting out to the field. But should we, at least in some instances, not mix those agents? Then when we go out from the containment into the field, should we keep release sites far apart, again, to avoid mixing these populations? So same idea, avoid the outbreeding depression, avoid the genes mixing when they're in the field, try to make it more difficult. And finally, should we avoid swamping a single site with repeated large releases? What we would tend to do now is that if we release agents at a site and there are signs of potentially establishment, but perhaps not doing very well, our tendency would be to put more agents into that site to help them out. But perhaps we're not helping them out. Perhaps we're actually preventing those adapted phenotypes from expressing themselves faster. Those are all questions that we would have to look into. Lastly, I've promised to talk a little bit about the other side of the coin, and that is about adaptation of the plants to the pressure from the biocontrol agents. We assume that when weeds invade a new environment, they are released from their natural enemies that they have in the native range, and they therefore have a chance to become a lot worse in the invaded range. But then what happens when they are reunited with those natural enemies, when we bring them as biocontrol agents, and how do they respond to that renewed pressure, the selection pressure? The system that we work on for this question at the moment is nodding thistle. And you see here in the picture, Melissa, she's a PhD student at Auckland University working on thistles and selection pressure from biocontrol agents. Thistle, nodding thistle, is a plant that when it flowers, it ends its life. So it flowers once in its lifetime and then it dies. But before it flowers, it can grow as a rosette for several years. And the longer it grows, the bigger it grows, the more flowers will come out of that, the more flower heads and the more seeds. So the reproductive success would be higher. But the thistles can get triggered to flower at a smaller size or at a larger size. And what triggers that? We don't quite know. And the empirical evidence, a little bit of an empirical evidence we have is that at sites where the nodding thistle crown weevil is at high density, the thistles might be flowering at a smaller size. And could that be an evolutionary pressure from the weevil that causes the thistles to flower before they have a chance to die? So if they don't flower in the first year, they might not get a chance to flower at all. And so do they get triggered to flower at a smaller size? Melissa was able to collect seeds and receive seeds from regional council staff from sites where nodding thistle is growing either with or without the crown weevil. And she's growing all of these plants in a common garden site at Lincoln. And at that site, those thistles are protected with insecticides, so they're not exposed to any biocontrol pressure currently. And what we're looking at is whether they choose to flower, they get triggered to flower at a smaller or larger size, and is that related to their history with exposure to the crown weevil. And I can tell you already that there are thistles in that plot that flower at different sizes, and it will be really interesting to match those size of flowering to the source of the seeds and whether they came from pressure or no pressure from the crown root weevil. So this is still a watch this space and not very long to wait. And that is really my last slide here, just a couple of thoughts for the future. We acknowledge that rapid evolution is part of weed biocontrol systems, both from the side of the biocontrol agents and from the host plants. we really are only beginning to scratch the surface in appreciating the potential importance of this area for weed biocontrol systems in New Zealand and probably globally. And it's very clear to us, though, that the consequences of rapid evolution can be significant for environmental safety, as well as effectiveness of weed biocontrol, which is exactly what we're working on, safety and effectiveness. And so it's a very suitable area for us to grow our research on. Thank you.
Excellent, Ronny. Thank you very much. So everybody who's attending, if you have any questions, please type them into the question box on your screen in the chat area, and I shall ask Ronny those questions. Ronny, I had one myself. One of the things I may have missed, because I'm an old guy and I can't always get the hang of these things. The sites that you were looking at Tongariro that had not been overrun by the advancing front of beetles, were those sites redistribution sites, or were they the original release sites of the beetles done in the very first releases?
Some of the sites where the new foci were starting to appear spontaneously without an intentional release, some of them were sites that had releases in the 1990s, in the early releases, and those releases failed in the 1990s, but now suddenly the beetles are spontaneously doing well there.
So this is something that I've seen before in work that I've done with releasing some of the gauze agents in particular, where we thought the original releases had failed, and so we've either made re-releases or we've sourced material from elsewhere in the world and re-released. And when we've gone to do that, we found the original releases had established after all, and probably become adapted to the new, to the climate eventually. So I guess this is kind of what's occurring here. But it's very interesting to see that if you wait long enough, then it seems often that the releases that you make almost always establish. Yeah. Okay. We still haven't got any. Oh, hang on. Do have a question here. Why can't I see that? Oh, actually, it looks like we have a few. So, where were the heather beetles sourced? Rod Hitchmo is asking that.
Yeah, so the original ones, or the only ones, came from Scotland.
Cool.
That is an area where the climatic fit was thought to be suitable for the areas of infestations in New Zealand. That was the reason.
Cool. How much is known about essential symbionts like gut microbes of heather beetles? Claudia Lang is asking this.
Oh, thank you, Claudia. Not a lot, not a lot. Another big area of research under the same area of improving safety and effectiveness of weed biocontrol is the area of understanding the microorganisms that are associated with biocontrol agents, and that can include both beneficial and pathogenic microorganisms. No answer.
It's some work we've been. So it's some work that we've been doing a little bit on with the green thistle beetle, I think, Castor rubiginosa. I think we were looking at some symbionts in those a couple of years ago, I think. But there's some new work we do find quite interesting. So yeah. All right. Another question is, in the slide with the heather pictures, were the heather plants killed or just defoliated? So therefore, so the other side of that is, are the heather beetle killing the plants?
Yes.
That's from Phil Lester.
Yes, they do kill the plants. Yes.
Okay. So Michael Bartlett,
I would take that opportunity, actually, Phil, to give another plug for Paul's talk tomorrow, because Paul will show you, a bit of a spoiler alert, what happens as a result of the heather getting killed and what comes next.
Yeah, dead right. Another one from Michael Bartlett. Are there collections of heather beetles from different time periods so that molecular work can be done in the future?
There are heather beetles. Every time that we release biocontrol agents, there are reference specimens deposited in the collections, and there should be beetles from later on as well. Not a high number, so yes, if those molecular tools ever do become available and affordable, we might be able to look at something, but it wouldn't be a large number of specimens. We could go to the native range and look at the source populations. We know exactly where those beetles came from, and perhaps we can expect that there were fewer adaptations and fewer evolutionary changes in those source populations. We could always go back there one day when we can travel again. But actual specimens from the times of release and throughout the decades, there are some specimens.
If I can just add in there, it is something that we've started doing more of more recently than we ever used to. So in our early days of doing this work, we always kept reference specimens for the New Zealand arthropod collection as part of our requirements for our standard import health standards. But we didn't keep specimens in alcohol for molecular analysis because no one was doing that work back when we were in these early days, but we are now. So we do have reference material available, which is being stored in alcohol for many of the importations and releases that we do. Ronnie, another question from Edward Barry. I wanted to ask whether heather population size and density was investigated as a variable that had an effect on beetle establishment success.
So the size of releases, the original releases, yes, so we do keep a log of the numbers that are being released at each release. And so in the original releases in the 1990s, there was absolutely no correlation between whether releases were large numbers of beetles or small number of beetles. They pretty much failed. In the, yep, what were you going to say?
Sorry, the question from Edward was not so much about the size of the releases, but the density of the heather population, which I think we did mark on the release sheets when we did that, but I think that was measured.
It is usually part of the release sheet, so there's a rough estimate of the density, and we tend to release agents in areas of high density of the weed. So that's kind of an assumption that
yeah, the density
where we choose to make initial releases is our areas where there's going to be no shortage of food.
Yeah, it's true. Yeah, we used to on our release sheets. One of the things we do mark on there is the density of the plant at the release site and nearby. So there's kind of an estimation of what level of population of heather there is. But it's not one of the variables that I think you've been looking at in terms of the rapid evolution work, though, Ronnie.
No.
Cool. And I think that was it. I don't think we have any more questions. So that looks like that's it. Thank you very much, Ronnie. It's some really interesting stuff. And thank you everybody for coming along and attending. We have another one of these talks this afternoon, which is from Simon Fowler, I think, is on this afternoon. But really good stuff, Ronnie, and we'll look forward to perhaps next year hearing some of the results of the work that you guys are working on. So
thank you.
Okay, thanks a lot, everybody.